Okay, so for our second talk today, we have Yongchun Chu. Yongchun is a PhD candidate at Columbia University and a graduate research assistant at LEAP, working with Professor Pierre Tintin. His work applies machine learning, generative modeling, and differentiable programming to atmospheric boundary layer turbulence and data assimilation. He holds a BS in mathematics and applied mathematics, as well as an MPhil in atmospheric environmental science. He is a simulation intelligence resident at Pasture Labs, advancing scientific machine learning for physical simulations.
And thanks for the introduction. And today I'm going to talk about our research work on towards prism-fault integration of variational data simulation and generative models. This work is in collaboration with Matthew and advised by Sarah and Pierre. So when we talk about the application of generative models, we always start from a perspective that we want to build a whole posterior distribution with generative model and perform sampling to achieve our target downscaling data simulation. But today we'll be introducing a different perspective, which is from an optimization perspective. So to this end, we'll be introducing the problem setup and the tools we'll be using, and then it will be the main algorithm, and we'll introduce a little bit the experimental results. So first, let's talk about a static inverse problem. So in a relatively general setting, in inverse problems, we aim to recover some unknown signal X from some noisy and incomplete observations generated through this observation, I forgot to turn on the timer to generate through this observation process, or people say degradation process, or some of machine learning community is a forward process, but we won't be using forward here. From this equation, there H is a possible nonlinear observation operator, and the dimension of the space of the observation space is usually lower than the dimension of the signal. And so the observation processes has some additive observation error. There are some examples, mostly the application of static inverse problems. They apply these different approaches to solve image problems, like super resolution for downscaling, denoising, and impacting. So we write down the variational formulation of to solve this inverse problem. So using Bayes' theorem, you can just decompose this posterior distribution, and taking the negative log of the posterior turns the maximum posterior problem into its equivalent minimization problem. So here you want to minimize this objective function, which is a sum between two terms. The first one is called the data fidelity, and the second one is the prior term. So this minimization, you can understand this R as a prior in this Bayesian formulation of the probability formulation. But in the minimization problem, this prior act as a regularization to the original problem, because if you look at this Y, as we mentioned, is of lower dimension. So if you ignore this prior term, it's like an EO condition optimization problem. So you have infinite amount of solutions. So here we need a regularizer. So if we have some knowledge about the noise in the observation processes, we can write down the FX explicitly, like Gaussian noise or Laplace noise, which is used to model relatively heavy tail noise distributions. So for variational data simulation, we first put physical time inside the whole inside this objective function. And what distinguishes data simulation from a static inverse problems is now we have a dynamic model app here used to propagate the state. And usually this model is imperfect. For example, we have limited computational power. We have to do prime transitions for different processes. We have spatial and temporal discretization errors. So anyway, even if you start from a real true state, the prediction will be drifting away from the underlying system. And now we kind of at every time step when we have an observation, we try to solve a static inverse problem with the background, which is the prediction generated by this imperfect forecast model and some observations, and solve the static inverse problem. We try to find the analysis works as a better initial condition for your following prediction. So here we talk about the R term as a prior. So the dynamic model gives a natural suggestion of prior. So somehow we believe the true state should not be too far from the background. So if we assume the true state is just, is normally distributed around this background term with some background error covariance, and we use the Gaussian noise for observation process, we can write down the optimization target for 3D variational data assimilation. The first term is the F term in the optimization, and the second term is the R term. And the same reasoning extends to 4D variational objective over a simulation window, but it only modifies the F term, the data fidelity term. And in this research, we focus on the R term because the Gaussian assumption on background error is a very arbitrary assumption. Even if at the initial step you have a Gaussian error, but as Jay mentioned, the model is super nonlinear, so the error won't be Gaussian for after a couple of steps. So the Gaussian assumption is like a very rough approximation. And non-Gaussian data simulation is an active area of research. And with machine learning, we're going to see what we can do with machine learning. Yeah. Feel free to interrupt me if you have questions. So let's see. So I think this is one of the first couple of papers try to use generative model along with the variational data simulation to tackle the non-Gaussian background distribution. So we can discuss details in the Q&A session, but the general idea is like you use a variational autoencoder to model the non-Gaussian background error to map it into a Gaussian latent distribution, and you perform the data simulation in latent space, and then you project it back to physical space. And with some derivation, the objective function looks like this. Like you just do gradient-based optimization for this one, but it turns out there's some difficulty to optimize the theoretical objective function. So they kind of have to ignore the whole term and try to rescale the term in the middle, which means you kind of need to modify the R term. It possesses some potential issues, like we can talk about later. There are some takeaways. The first one is don't use variational encoder, but yeah, we'll talk about this later maybe. But the second one is like it's a little bit hard to if a machine learning model involved, it's a little bit hard to term and the R term together and take gradient to do gradient descent. So what we're going to do is to divide and concur the two terms, F and R. So in optimization, there are a set of established optimization algorithms called proximal splitting methods, which is basically you try to split every iteration, like steps into at least 2 steps. And the first, you use the first step to deal with this F, use the second step to deal with this R. A very simple one, a very simple example is called forward-backward splitting. So this is an algorithm. You can see in each of these iteration, first you do a step of gradient descent along the data fidelity term. Normally you have a pretty well-behaved F, like for example, we mentioned the Gaussian is like a 2 norm of something, it's like smooth. And the second term you perform, it is called a proximal step on this X. So how to understand this proximal step? So essentially it's an extension of projection, but it sounds a little bit abstract. We have 2 interpretations of this proximal step. The first one, it is the best estimate of your X given your prior R and your current intermediate optimization step. It gives the based on these 2 information is the optimal estimate. Another one, if you look at are familiar with the inverse problems, this formulation is actually a denoising formulation with the Gaussian noise. It's an W. So yeah, but to do this, you have to have an explicit form of your prior. But we want to do machine learning. We kind of sometimes we don't have this explicit prior, and people extend these proximal splitting methods to plug and play framework, where we replace this proximal step. We know it is essentially a denoising step, so we can use independently designed denoiser or even machine learning learned denoiser to perform this denoising. So it has nothing to do with the gradient-based updates. So here is like people use deterministic machine learning to do this denoising, and recently people have been working on extend this denoiser to generative model-based denoiser. And recent works includes a diffusion-based denoiser and flow matching-based denoiser. And here we prefer flow matching-based denoisers due to some like theoretical elegancy of flow matching compared to diffusion. So here is a very recent paper. It's actually presented several weeks ago. They use a flow matching as a prior to design this denoiser. So to explain a little bit of flow matching, let's just ignore these arrows. So essentially, flow matching is to find a probability path between your reference distribution, which is usually very it's very trackable, like a Gaussian distribution. You kind of transform this latent distribution to your data distribution along some probability path, and you learn the motion along this process from whose velocity is parameterized by a neural network. After you learn the velocity, like you can sample from the latent distribution to solve the ODE of movement with this learned velocity, and you reach your target data. And through this process, you can do sampling. So this is basically full matching. And as I mentioned, we won't be talking about sampling, but we will see how it works with the PNP framework. So basically, if you remember, the first step is to take a gradient step with respect to your observation. So with the random initialization, you take a gradient step to your optimization. And then the second step is the denoising step. They use this flow matching based denoiser to map this intermediate step back to the data distribution. But the issue here is the flow matching based prior works better along the probability path. But after the gradient step, you're probably landing outside of this probability path. So you somehow need to interpolate or push it back to the probability path. So there is an interpolation step. So you kind of move your intermediate step back to the probability path, and then you perform this flow matching based denoising, and you do this iteratively, and you reach your target.
Is it principle the interpolation step to get back to the latent space, or is it how do they?
How do they prove this? This is the only issue I have with this paper. But it turns out it works, and I'm actually trying to explore this one. Just try to prove, because the probability path is a straight line, like path. So it should be, if we're able to prove it, it won't be that difficult. But they didn't analyze this step theoretically, like rigorously in their paper, but this is definitely what we need to think about it. Yeah. But the similar idea is the similar idea of this interpolation step. It is like used in several papers, like the gradient-free paper to enforce constraints. They also use this interpolation just to map it back to the probability path. So here they use this prior, which is an unconditional prior, and we want to make it conditional, since we have a huge amount of historical reanalysis and background data. And with data assimilation, we do want to incorporate background to make the whole thing more flow dependent. So here we introduce our algorithm. So the first step is the target is to build this kind of prior. With this prior, we will be able to sample from the conditional probability given any background state. So the tool we're using is called the optimal transport based on patient flow matching prior. It looks crazy, but anyway, we want to find the optimal transport plan that achieves this conditional Wasserstein distance, which has some theoretical guarantee that we're able to sample from a conditional distribution. But essentially, so it's this optimal transport plan try to transport the joint distribution of your background and your reference distribution to the joint distribution of your background and your analysis distribution. If you are able to achieve this conditional Wasserstein distance, it will keep your background distribution unchanged while moving from the reference distribution to analysis distribution. So essentially, they're modeling the conditional distribution. So then we define the interpolant of this flow matching, which is a straight line flow. That is why we prefer this flow matching over diffusion, because in diffusion you don't have mostly you don't have straight line flow, which makes the whole thing more involved. Then we train a flow matching model with the following laws. So this is the velocity field parameterized by a neural network. So this neural network intends to there is some theoretical analysis like what is neural network representing, following the similar with this straight line flow property and following the similar argument from some theoretical paper on flow matching. So in fact, the neural network we're training is trying to reproduce the best in terms of an expectation perspective, the velocity of this field given your intermediate background step and given your background and the intermediate sampling or optimization step. And then we define this denoiser by this one, and we plug this the interpretation of this neural network to this equation. And with some easy derivation, like they're using some linearity of this expectation and the definition of conditional expectation, you can actually derive the interpretation of this denoiser, which is the expected value of your analysis given your background and your intermediate sampling or optimization step. This is like exactly the same we mentioned in the forward backward splitting. We want to solve the best estimate of your signal given your intermediate step and prior. So this is exactly the same. So that we just put all of them together. We perform. We will have this. Then we have this data assimilation analysis step. In 3D version, we first perform this gradient descent along the observations, and then we interpolate it back to the probability path, and then we use this denoiser to forward it to next step, and we do this until convergence. And you can see this machine learning has nothing to do with the gradient step, so it's very easy to extend it to its 4D version. So we just need to modify this F term without changing everything else, without retraining the neural network. And then I'll show you some experiments. We're testing these algorithms on toy problems, 2-scale Norris 96, where we assume the true system is this 2-scale Norris 96, and we use the 1-scale Norris 96 as a forecast model of this 2-scale Norris 96. This is to mimic the situation that we have missing physics. Anyway, we want to have a bad model compared to the truth. So we have this model as bad model. So we are using 8 solo variables, and we have some very sparse spatial temporal observations, and we generate historical analysis and background pair with ensemble common filter as the training data for the OT Bayesian flow matching. And this is like we perform cyclic data assimilation forecast. And compared to the optimal solution of 3D Variational data assimilation, we're able to have a better trajectories. The black dots are observations. And this model seems to be robust against observation density. So we repeat the cyclic data assimilation forecast experiment several times. So here we have this error bar, and we test the situation where we have different number of observations from one to like only one observation to like full observations. So this PMP-based method is consistently better than 3D Variational data assimilation. And we can see some convergence here. It is very reasonable since here we have full observation. So basically there's no need to have a good prior. So you basically observing the whole thing. So yeah. And this method is also robust against observation noise level. Oh, by the way, the training data is generated with the 4 observations. Yeah. Sorry. So here the training data is generated with the 0.5 observations noise standard deviation, and we tested on different to increase the noise, and the PMP is still consistently better than 3D Variational data assimilation. So the RMSE is calculated along the trajectories. So in conclusion, we developed a data assimilation method that is robust and flexible, and it is computationally efficient compared to other variational data assimilation and machine learning methods. First, the computation is fully like trackable, and we don't need to. It only requires forward pass over neural network, and we don't need to take gradient with respect to trained neural network during the gradient-based optimization. So it is relatively more efficient. And yeah, it is relatively more principled because every single component from this algorithm is kind of very based, except for the interpolation step we're still trying to look into. And currently we're working on some 4D data assimilation experiment, and also try to test these methods on more complex systems like 2D flows. And we're trying to do this convergence analysis that is almost there. It is under some assumption, you can show that the sequence generated by this optimization process is a Gaussian sequence. So you have a limit there. So yeah, that's all my presentation. Thank you.
Can you show again the algorithm with the recursions of the 2 algorithms?
You mean the
first
figure?
The first ones of PNP and
This one?
before.
The forward backward splitting.
Yes. In these algorithms, there's no control on the slackness between X and W. Like in ADMM, for example, you would allow some residual between W and X, right, with the Lagrange multiplier.
Yeah.
You could also do that here with the noise with the neural network, right? In principle.
Yeah. ADMM is an advanced version of proximal splitting method. So
it might be that this
beyond this level.
It can improve the problem of interpolation to allow for some slackness between like to not harshly project, maybe.
Yeah, this is not a harsh project. This RX, you can have some design there to make it less harsh. If it's a projection, this is the indicator function.
Yeah.
But this is not a projection here. You can have some relaxation in this design of prior.
Okay, thanks.
In terms of compute, how does it compare with the other method?
In fact, I didn't try because I didn't try other method. The optimal 3D var is like faster, I would say, because you have the analytical solution. But if we're doing, I mean, gradient descent, I don't know. It's like Yeah. You don't need a lot of steps to reach convergence. In fact, like I tried several, like 200 steps, 100 steps, there's not too much differences. And with 100 steps, I don't know whether gradient descent will converge. For example, for the variational assimilation. Yeah, that I don't think it's a big problem. For current scale, like if it's a full scale mathematical, I'm not sure. Oh, yeah, this question is like, for efficiency, did you mean that the gradient computed from your network is much more efficient than Jacobian computation in normal case? So it's actually two questions. If, for example, if you have you have a neural network in this, let me show. When you have a neural network in this R term, and you want to do gradient descent with respect to the whole thing, you have to take gradient with respect to the neural network, which makes the gradient super complicated. It might be affect the numerical stability. And in terms of the Jacobian computation is another story. Yeah, I can take this opportunity to explain a little bit. Even before taking gradient, this computation is hardly trackable. It's because like you have an arbitrary encoder. If you want to drive the D has to be bijective. Otherwise, you cannot. You don't have a you won't have a non-singular Jacobian matrix, which means the determinant can goes to 0, and the log will goes to negative infinity. Before taking gradient, the whole thing is computationally infeasible. That's why they have to come up with this simplification to remove the whole term of log determinant of Jacobian. And this is actually not a new argument. It's actually an old story. Like 10 years ago, when people tried to do rational inference with a neural network involved, they figured out, okay, it's very hard to calculate this log determinant of Jacobian. That's why they developed the specific like invertible neural network and normalizing flow to make the whole thing trackable and to be able to perform variational inference. So it seems like there is a low-hanging fruit. You replace the variational encoder with the normalizing flow and just you got a new paper. Yeah. So that's the two parts of the computational efficiency I want to mention.
At time, so thank you so much for this great presentation.